Hi everyone, we will be presenting a project on probabilistic forecasting with deep autoregressive neural networks. Unlike point forecast that associates the future with a single outcome, probabilistic forecasts allocate a probability for different events to happen. This is well suited for applications like capacity planning and demand prediction and helps in decision making under uncertainty. In our work, we are forecasting stock prices, which is a challenging task due to unstructured, chaotic data and complex group-dependent behavior. To capture correlations between multiple time series, we model stocks of multiple companies jointly. But that also comes with challenges like the magnitudes of these time series can vary widely. DeepAR overcomes these challenges by learning a global model using auto-regressive recurrent neural networks. Also, it does not require extensive feature engineering and is able to capture seasonal patterns. For our baseline, we implemented DeepAR from scratch. We divided every time series into a conditioning and prediction range. The time series is known in the conditioning range, whereas in the prediction range, at every time step, we sample a value from the Gaussian distribution parameterized by the output of our model. Information from the conditioning range is transferred to the predictioning range via the hidden states. But unlike a sequence-to-sequence model, the encoder and decoder use the same architecture here. To train the model, we use negative log likelihood, and the metrics used to evaluate the performance were RMSE and ND. The results are as follows. In all the figures, the vertical black line demarcates the end of the conditioning range and the beginning of the prediction range. The red curves indicate the predicted values, whereas the blue curves indicate the original series. As we can see in the top two plots, our model is able to accurately predict the stock prices. However, as seen in the bottom two plots, the model fails to even capture the trends. Additionally, in the top two plots, we can see that to minimize the loss, the model tends to predict previous day's price. To tackle these problems, we propose three enhancements: deeper horizons, higher auto-regressive context, and vector inputs. To disincentivize the model from predicting the previous day's price, we propose a deeper horizon loss weight function that considers the labels of future time steps while calculating the loss. From the results, we can see that this deeper horizon learns to predict the overall trend instead of just predicting the last time step. This results in a much smoother trend prediction. Secondly, we train a model with a higher auto-regressive context as inputs. The motivation behind this was to complement the LSTM's ability to remember. Overall, we got a better RMSE and ND performance compared to baseline through this model. Lastly, to further enhance the model's ability to capture common trends, we group the company stocks based on sectors so that the model takes as input a vector of time series and outputs a vector of Gaussian parameters. This example result plot is an output of vector of 3 time series. Here, the model is able to predict prices of some of the companies in the group, but fails to generalize well on other companies. We believe that our assumption that companies of the same sector follow similar trends does not necessarily hold true. From this table shown on the right, we observe that models with larger context are able to outperform DeepAR on the RMSE and ND metrics. Also, our deep horizon loss function shows significant improvement in predicting trends, whereas the vector inputs approach seems ineffective. To improve upon our work, we will derive better loss function and metrics to capture trends that rather than point-to-point distance. Thank you.